Ladies and gentlemen, today's lecture is going to be on tensile testing. Tensile testing is the most important mechanical property testing. And I'm going to divide this lecture into the following. Number one, a short background. Number two, the test itself. And then number three, analysis of the data that we get from the test. So let us start first with the background. In the background, why is tensile testing the most important test? This is because it is the most severe test. So all materials have in them cracks and defects. If you pull a sample in tension, then what happens is these cracks are going to propagate, expand, until the largest one of them will break the sample in two. Now, if you're doing compression, then what will happen is that the cracks are going to close. The cracks will close shut as compared to the tension where you have propagation of cracks. What about bending? Bending is going to be such that you will have a part in tension and a part in compression. So when you do the bending test, you're going to find that it is going to be weaker than the compression because a part of it is tensile. And it is going to be stronger than the tension because a part of it is in compression. So again, when we compare tension and compression and bending, we find that the tension is the most severe test. So this is for a simple introduction. Now, what about how do materials react to the tension test? Well, if you talk about a ceramic, like you learned in material science, is composed of covalent or ionic or a mixture of covalent and ionic. And that's why ceramics are brittle. So if I put the force in pounds or in Newton versus the extension in inches or millimeter, you're going to find that the ceramic is going to just go in a straight line and then it will break. So this part is what we call the elastic region, and I'm going to talk about it in a few minutes when I talk about metals. And we have no plasticity, no ductility, no formability in ceramics. Examples are high-tech ceramics like silicon nitride and low-tech ceramics like, say, concrete. Now, this is for a ceramic. What about for a plastic or a polymer? For a plastic or a polymer, we're going to have if I have force in pounds or Newton versus extension in inches or in millimeter, then I'm going to have, let me write the force digital. You're going to have a straight line region, and then you're going to have stretchability and ductility. And we're going to see this in one of the tests. And this is because, again, like we learned in material science, polymers have covalent bonds between mers, say like C2H4, which is ethylene. So you have something like this is a mer, and then you have other mers. So this is one mer, and this is another mer. So in between them, you have the strong covalent bond, but in the whole chain, where these are mers, each of these is a mer. The way a polymer is connected together is by having other chains connect to it, or connect with each other rather. And this let me take another color. This very weak attachment is the molecular, or the very weak, despicable van der Waals bond. So this part is the van der Waals or molecular bond. So at the beginning, you're stretching the covalent bonds, and then you're just overcoming the van der Waals weak bond. Now, in metals, the story is a little bit different, and we're going to talk a little bit more about what happens. So we're talking now in number C about metals or alloys, where an alloy is a metal with an impurity. Now, before we start, I need to define a couple of terms. Stress sigma, or stress, is equal to force divided by area. Why? Because force alone doesn't mean anything. If I have two bodies, one of them is like this, and the second one is like that, and I apply the same force, you're going to find that this body is going to be affected much more than this body. So what I'm trying to say is, for example, get two persons, one of them is like this, and the other is like that, and punch them with the same force. This guy is going to fall, and this guy is going to be tickled. So the force means nothing except if you define the area over which it's acting. So if I have sigma, which equals to a force in pounds, divided by n squared, or what we call PSI, pounds, square inches, this is defined as the stress, the action. We're going to define also the strain, which is the reaction. In the strain, we're going to think of it in this way. If I have two strings, one is like that and one is like that, and I pull them, or I stretch them rather, with the same initial stretch. One of them, so I'm having the same initial stress. This guy is like almost 30% stretched compared to its original length. This guy is maybe 5% stretched compared to its original length. So when we talk about strain, we have to again look at what are you straining. So I define it as delta, which is the extension, divided by the initial length. this is the initial length 1, and this is the initial length 2. So L naught is initial length. So as you see, delta divided by L naught, or extension divided by the initial length, will give you this frame. And this is clearly unitless. It is millimeter over millimeter, or it is inches divided by inches, or unitless. So now I'm going to look at these curves, which I talked about briefly, and I'm going to talk about them in connection to metals. And this will finish, well, no, still I have to define another thing. I'm going to define, actually I'll define a couple of things when we are in number 2. So we're done with the background, and we're going to talk about tensile testing, and I'm going to use these terms. In the background, we talked about how is the test, how is it performed, and then we talked about its effect on different materials, which is a reflection of the bond or the microstructure of the material. So now I'm going to talk about the test itself. The test itself is going to be performed by Mr. Jadong Sun. He's our lab manager, and he is going to get us samples like this. These samples are cylindrical samples. This is aluminum, this is steel, and this is high-density polyethylene. And you will notice that in the samples of aluminum and steel, there is a color. In the report, I'm going to ask you to, and I'm going to put this in red, the questions that you need to answer in the report. I want you to tell me in the report about the color code. What is it in steels? Because we're going to do a steel sample. And what is it in aluminum? Because we will do an aluminum sample. So this is one question that you need to address in the report. I'm not going to say it to you, you're going to get it for me. Now, depending on your work, instead of having a cylindrical sample, you can have a rectangular sample. We have several frames in the lab, and we have the capability of doing rectangular and the capability of doing cylindrical. So for example, if I'm provided with a plate, let me first write here that I'm going to talk about the tensile test. And I started by talking about the samples. And like I indicated, the samples can be cylindrical or they can be rectangular. So for example, if I have something like a plate and I rolled the plate, I rolled it, and we have a rolling machine, we're going to see it later, into a sheet, a very thin sheet. So the thin sheet, if you look at it from top, it looks like this, and then it's easier for you to go machine a rectangular specimen. If you have a thick plate and you want to test it by doing cylindrical bars, you can machine cylindrical bars. But especially when you have thin sheets, then you like to do rectangular samples. Okay? So the samples can be different. And when you see the demonstration by Mr. Sun, you're going to see the frames that we're going to use. In this experiment, we're going to use the Tenius, that's a company, Tenius Olson machine, and we're going to do cylindrical samples. And the steps to do that are as follows. The first thing, you're going to take your sample, and like I indicated before, it is a cylinder, so it has a circular cross-section. What you're going to do is you're going to measure the diameter. So you're going to get D naught, or the initial diameter. You're going to measure that. And you're going to see that these are standards. This is 1/2 inch diameter. And this takes me to the second question, where I'm going to ask you to include for me in the report a summary of ASTM American standard of testing materials. So you're going to get for me ASTM E8. So clearly you see how we have in our system different tests. ASTM E8 is for tension testing. There's another number for fracture toughness testing, another number for compression testing, another number for bending test. We have hundreds and even thousands of these standards. Why? You don't want somebody to come with like a sample which is 3/4 of an inch, and another person comes with a sample of 1/4 of an inch, and then it will be very difficult to compare data. So we have standards that we use. And the standard for a ASTM E8 is we take a sample, and the diameter is usually 1/2 inch, and usually this length is 4 inches, which is going to be you will see the standards. We like to keep the length as 4 times the width, and we have certain numbers that I want you to go and check them out for me and write a couple of paragraphs on that test. So anyway, Mr. Sun is going to measure for us the diameter, and the diameter should be around 1/2 an inch. Then he's going to come to the sample, and he's going to make a marking. He's going to mark here and here. He's going to put black markers here, and this will be 1 inch. Now, sometimes they take 2 inches, sometimes they'll take other numbers, but this will become evident later. We're going to call that inch as L naught, or the initial length. It is 1 inch, correct?
Yeah.
Okay.
It depends on the extensometer, the measure distance of the extensometer. Yeah. Some extensometer has 2 inches, 3 inches. Yeah.
Exactly. So after he does that, he's going to take the sample and go to the frame that we have. By the way, each of these frames cost over $200,000, and they are very sturdy, and they live for 30, 40 years with excellent accuracy. So first we talked about the samples. Then there is a frame. When you look at the experiment that Mr. Sun will show you, you will see the different frames. And in each frame there is a jaw or grip where we have the samples, usually the samples as you see here, they have a thread. So we're going to screw the samples into the grip, and we're going to have here, we're going to have here the two samples attached. The sample will be attached to the two grips, and then it depends on the frame. The frame we're using will have the upper jaw or the upper grip stationary and the lower one doing the stretch. In other frames, you have the top one doing the motion and the lower one being fixed. It depends. Anyway, you are going to have a tension load. And your output is going to look as follows. This time, notice I'm not going to talk about force like I did before. I'm going to talk about stress. Stress in pounds per square inch, or in megapascal when we use the SI units. Now in metals, we're going to find that there is thousands of pounds per square inch, and that's why we're going to use the term KSI, where KSI means 1,000, and implicitly it means thousands of pounds per square inch. So here you're going to find the term sigma in KSI. Now here we're going to have the strain epsilon, inch per inch, or millimeter per millimeter, or the way we like to do it, to put it in percent. Instead of telling you like I have a 0.001, I'm going to tell you that I have a 0.1%, just to make the numbers go a little bit smaller. So here, the strain, it will be again unitless, but it will be in percent. Now, when Mr. Sun operates the machine, you're going to find three regions. Region 1 is what we call the elastic region. This is called elastic region. So what is elastic region? Elastic region is the reversible region. If you take the sample and you stretch it, it will stretch with you. You release the stress or release the force, it snaps back to the original dimension. Now, this is extremely important. This part, we are going to take its slope. Actually, the computer does that. And if I take the rise over the run, or stress versus strain, or stress over strain, we're going to get what we call Young's modulus. Young's modulus, or the slope of the stress-strain curve, or in engineering slang, we call it the stiffness in tension and compression, is going to be the slope, which is sigma of the straight line, sigma over epsilon. And since sigma is in KSI and epsilon is unitless, then it will stay in KSI, but actually we find that the number is humongous. So we like to present it in MSI, where M implicitly means millions of pounds per, again, square inches. So what is the importance of this term? It tells me about the stiffness, about the how much the material is not compliable, how much is the material compact and stiff. It's proportional to the bond strength. I'm going to just very quickly on the side tell you about something about the stiffness, and that is, imagine if you have 5 identical samples of different materials. For example, if I have 5 identical samples of different materials and do the tension test. So if you do the tension test and stop at this elastic limit, and let's say that here I have stress in KSI, and I have the strain in percent, then the 5 different materials are going to look like this. One of them is like this, second like that, a third like this, a fourth like this, and the fifth like this. This is going to be diamond, the stiffest material on Earth. This is going to be steel. This is going to be aluminum. This is bones. And this is tendons or muscles. So as you see here, as you go in this direction, the slope becomes higher and higher, and you get stiffer materials. We like to use steel compared to aluminum when we have bearings or when we have springs that we want them to be very stiff. But we use aluminum compared to steel when we want something which is more compliant or more flexible or more light, lower density. So if you go on this direction, as the slope gets smaller and smaller, you get more flexible and compliant materials. Now, in mechanics of materials, they're going to teach you that E of steel is 30 million psi, and E of aluminum is 10 million psi. Or they will teach you that aluminum has 70 gigapascal and steel has 210 gigapascal. It depends on the units. Our machines, we program them in the imperial units, but then when we publish, we change them into the SI units. But as you see here, that the E of aluminum the E of steel is 3 times that of aluminum. That's why in cars, we use mild steel as the body, not aluminum. If we want to use aluminum and make it as good as steel, we have to make it 3 times as thick. But here for our work, let's say that I have the same force. I came and I kicked 2 panels, which are identical. One of them is made of steel and the other made of aluminum. So if this is the stress, this is the strain on the steel. So let's say that the stress was maybe 100 KSI. Then the strain on steel is this, and the strain on aluminum is this. And you can prove to yourself very easily that the extension of aluminum will be 3 times the extension of steel. So that's why we like to use steel, because steel, when you punish it, it's not going to extend as much as aluminum under the same force. Now, let's go back to the curve. When Mr. Sun do for us the test, we will be in the first region. First region, some people call it the Hookean, after Robert Hooke region, and some people like to just call it elastic region, And in it, when we do the stress versus strain, we get the Young's modulus. Now, the very important thing is that when you want to characterize a material, you do the tension test and you get 5 parameters. So we spoke about one parameter, and I'm going to say here that we need 5 parameters. So the first parameter we talked about is Young's modulus. Now, like if you have a rubber band, if you stretch it, it stretches with you. You release, it goes back. If you keep on stretching, like a rubber band was like this, when you keep on stretching and then it becomes permanently like that, then there is a permanent deformation. And this is what will happen in a metal if you keep on stretching it and applying the force, because stress, we agreed it is force divided by A naught. And what is A naught? A naught is what Mr. Sun has done for us. He took the diameter, so pi d squared naught over 4 is the area. So as the sample is being stretched, the software is going to take the force divided by the initial area, and it's going to keep on recording the stress. Now, at a certain point, you're going to get deviation from linearity. So this is a deviation. And guys, like, God forbid, if you were in a real nasty accident, and then you stayed the rest of your life limping. Now, at the beginning, when you are at the accident, you stay for a couple of months in very bad shape. But as time goes on, you are going to recover at least 80 to 90%, but there is a percentage of permanent damage. So what scientists have agreed to work on is the permanent damage which a material will reach. And what they decided is to take a strain of 0.002 or 0.2%, and they're going to draw a line parallel to the elastic line, and they're going to intersect here, and they are going to mark this point and call it sigma y or sigma yield. Now, notice that the sigma yield is going to define for me the following: sigma y or sigma yield or 0.2% offset, all means the same thing, and all this is going to define this term. Somebody will say, why is that important? You see, guys, when we design, we want to be inside the elastic region. You don't want to drive on a road and then after you went over the road, you look at your mirror, rear view mirror, and you find that the road permanently deformed. You want the road to elastically deformed while you're on it. When you leave it, to snap back. You want all your structures, whether an aircraft, whether a bridge, whether any structure, yes, to deform elastically, but then when the force is not over it, not on it, to recover. So if I know what is the stress that will cause the slightest permanent deformation, permanent, then I'm going to design to have the actual stresses, the weight of a truck, the weight of a car, the weight of anything acting on the bridge, that it has to be within the elastic region. Anything acting on the airplane, it's within the elastic region. So if I know the sigma yield, I will be sure to work with a external stress below than the yield limit. So we always like to design sigma external to be less than sigma yield to stay in the elastic region. And as a mechanical engineer, you always want to stay within the elastic region. Now, if you keep on testing, you're going to find that you reach a peak and then you go down. Actually, when you look at the sample here looks like this. The sample here still looks like this because you can't really detect with your naked vision that the sample is changing. But when you reach here, you're going to see that the sample will start necking. And when it starts necking, it tells you that it is about to break here, and then the neck is going to get smaller and smaller, and then at the end, the sample will break. This is the last fight that the material can do. And this last fight is where we're going to define it as ultimate stress, sigma ultimate. So what is sigma ultimate? Sigma ultimate is the ultimate or highest, or some people call it tensile strength. When you later study fatigue, you're going to see how important this is, because the strength of fatigue is usually half of the ultimate strength in steels and about 1/3 of the ultimate strength in aluminum. But for our purposes, as undergraduates, we need to know it is an important parameter. So up till now, we talked about Young's modulus, we talked about the yield strength, and we talked about the ultimate strength. If you buy a piece of material, the manufacturer has to give you these parameters. They have to do random testing for the product, and they have to give you these parameters. This talks about stiffness. This talks about permanent deformation stress. And this will talk about the ultimate or the final strength before the material fractures. Now, let us see why did Mr. Sun do certain measurements. Let me erase that part. You remember I indicated that he put a marker. Why did he put the marker? Sorry, in fact, I forgot to tell you that what he's going to do is put a marker here of 1 inch. And I forgot to tell you that he's going to connect an apparatus, which we call an extensiometer. What is that extensiometer? It is a device like a strain gauge, which tells you that the material is stretching, extending. We know that epsilon is delta divided by L naught. And the L naught is the 1 inch. And like he told us, extensiometer have different grades. You can do it with 2 inches or 1 inches. We'll do it with 1 inch to make our life easier in calculations. So what he did was, he put here these two markers, and he had here the extensiometer. While the sample is stretching, the extensiometer is measuring for us the extension, and the software is dividing the extension by 1 inch and calculating for us the strain. Now, we are going to define a fourth term, which we're going to call it ductility. And that fourth term is LF minus L naught divided by L naught. LF is the final length, and L naught is the 1 inch or the initial length. So what happens is, as the sample breaks, Mr. Sun is going to come and put the sample together, and he's going to measure the distance traveled by these two markers. These two markers were at 1 inch away from each other, but as you're stretching, they move apart. So this is going to be your final length. So assuming that the final length is, say, 1.5 inches, and your initial length was 1 inch, so your ductility, or we like to call it percent elongation. Your ductility or percent elongation is going to be 1.5 minus 1 divided by 1. So it's going to be 50% elongation. So this is the fourth thing that the manufacturer has to provide you with. What the manufacturer does, they take random samples, and they take like 3 random samples from different random locations of the plate or the cylinder, and then they will measure for us the 5 parameters. The fifth parameter is special. Why? Because only you can do it if you're doing cylindrical samples. Why? Because if you take the initial sample and you measure the D naught, which is what we have done, D naught was measured, and then we use it in the area, and after the sample breaks, you measure the final diameter. This is final diameter. Then, what you're doing is your, what we call it, percent reduction in area. Reduction in area is going to be A naught minus AF divided by A naught. A naught is pi d squared naught over 4 minus AF pi d squared F over 4 divided by pi over 4 d squared naught. And when you massage it, you remove the pi's, remove the 4's, it will become percent reduction in area is A squared naught minus A squared F divided by A squared naught. So This is the fifth parameter, if and only if he's doing a cylindrical samples. So if he's doing rectangular samples, we do not get that fifth parameter. Now, we looked at the tension test, and we want to take a look at the couple of things in the analysis. So in the analysis, you're going to see that the curve that Mr. Sun will give you, we'll talk about the analysis. So first, I'm going to talk about the stress strain curve, and second, I'm going to talk about fracture. So the curve that Mr. Sun will give you will look like this. Stress, KSI, and here percent strain. And it's going to look like this, like this, like this, and then like that. Why is this? This is because when he reaches the deviation from linearity and the material is being stretched and stretched, he's worried about the extensiometer. Because if the sample breaks, the extensiometer can go hit the wall or the floor, and the extensiometers are around $3,000 each, or even more, if you have like 1 inch grade and 2 inch together in the same thing. So we're afraid to break our samples. So a recording will tell him after he reaches a point somewhere here, a recording will tell him remove the instrument. He will remove that. So when he removes this, we don't have any more x-axis. We only have a y-axis. So the material will reach the sigma ultimate here, and the material will reach the sigma fracture here. So if I look at what should be stress versus percent strain, it should be like this. So this is the sigma ultimate, and this is the sigma fracture. So we're going to see it like you're going to read here the ultimate and here the fraction. Of course, the software is going to draw a line parallel to the straight line here, and it will tell you that this is the yield strength, and here is the 0.002. So what I'm trying to say is that it will not mess with the yield strength, but because we remove the extensiometer here, before we reach the ultimate, you're going to see an upper point and the lower point. Last thing, you remember I requested you for 3 questions. Question 1, which is the code. Question 2, which is the ASTM E8. I will send it to you, and I want you to summarize it. Question 3 is fracture surfaces. I want you to tell me about how, and this part is in the analysis, how when you break a sample, sometimes you're going to get something looking like this. Sometimes you're going to find it different. And I'm sending you the pages which talks about the coupled, the cone, and the brittle fracture. I want you to see that one of the tests that we're going to do for the high density polyethylene, I'll give you the results, but you're going to see that our sample was not able to break it. I mean, our machine was not able to break it. It extended by, I think, at least 2 to 3 times its original length. So I want you to tell me also why a polymer keeps on stretching. So these are the 3 questions that I want you to include in your report. This is a recorded lecture. So when I meet with you and after we listen to the lecture, you can ask me questions about the questions that I'm asking you or about the lecture itself. Thank you for listening.